In this video, we will learn about total internal reflection and critical angle. See, we know for a fact that when a light travels from an optically denser medium to an optically rarer medium, say a light is traveling from water to air. In such conditions, a small fraction of light travels back into the denser medium on account of internal reflection, and the remaining light is refracted to the rarer medium. As you can see in this particular case, when a light ray falls obliquely on a surface, some part of it is reflected back and most of the part is refracted. Now, let us consider a plane interface x dash separating a rarer, that is air, from a denser medium, that is water. Now, let point O be the point object situated in the denser medium, this one. Now, a monochromatic light OA1 incident normally on the interface is refracted into the rarer medium straight along OA1 R1, right? As it is incident normally, it will not bend in any particular direction while changing the medium. Now, another ray of light OA2, this one, incident obliquely at a small angle of incidence, that is I1. This is angle of incidence I1. Now, a small part of the light is reflected back, that is A2 B2, and the remaining light is refracted in air, that is A2 R2, with an angle of refraction R1. Okay, from this we can easily say that the R1 is greater than I1, because while going from a denser to a rarer medium, light tends to bend away from the normal. So this angle, that is the R1, would be bigger than this I1 angle. As the angle of incidence I is gradually increased, the angle of refraction R in the rarer medium also increases and increases at a faster rate. Now, for a particular angle, that is the critical angle, when I becomes equal to the critical angle, the refracted ray travels just along the interface, and that is now the angle of refraction has become 90 degrees, as you can see in this particular ray diagram, right? Now, in figure OA3, that is OA3, this one, angle I is equal to angle C, where C is the critical angle. You can see at the critical angle that the refracted ray is just gazing along the interface and the angle of refraction is 90 degrees. Okay, so as you can see that A3R3 is just gazing along the interface. Now, this angle of incidence, that is C angle, is what we say critical angle for a given pair of media. The critical angle for a given pair of media for a given monochromatic light is defined as the angle of incidence in the optically denser medium, for which the angle of refraction in the rarer mediums becomes 90 degree. Now, this is the definition that you will write if the question is asked about what is the critical angle and how will you define it. If I further increase the angle of incidence more than the critical angle, then there will be no refracted ray and the whole light gets reflected in the denser medium itself, as you can see in this particular figure. So in figure you can see that OA4, the angle of incidence is more than the critical angle. So the complete light is reflected back in the denser medium as A4 B4. Yes. So this phenomena is what we say total internal reflection. Therefore, total internal reflection of light is a phenomenon of complete reflection of light without any sort of refraction taking place when a light ray traveling in an optically denser medium is incident at an interface with a rarer medium at the angle greater than the critical angle for that pair of medium. In total internal reflection, 100% of the incident light is reflected back and there is no loss of light whatsoever. Now, what are the conditions for total internal reflection? See, there are two conditions. First, the light ray must be traveling from an optically denser medium towards a rarer medium. The second is that the angle of incidence at the interface must be greater than the critical angle for the given pair of media. I hope this topic is clear to you. Thank you.